Good morning, everybody. Bright and early here, last day of the show. Thank you for coming. I'd like to introduce myself. My name is David Domkin. I work for a company called UCC Environmental. This is a privately held corporation that's been in existence for 104 years. Most of our existence, we served the coal-fired power industry in the business of moving material, specifically fly ash and bottom ash, and building systems that get that material.
Well, thank you to those of you that stuck around. My name is Jake. I'm a licensed geologist with SCS Engineers out of Wichita, Kansas, and I'm going to talk about deep injection wells as a wastewater management option with a little bit of focus touching on like CCR, leachate, and so a few considerations for power plant facilities. But I'm going to start off with a pretty injection well 101 heavy part of this, because as we engage potential clients on these kinds of projects, we find that a lot of people just haven't been exposed to this technology, haven't had the chance to learn much about it, or worse yet, they have misconceptions about what it is or how it works. So, the green box didn't show up on here, but whenever I say deep wells or injection wells today, I'm talking about class 1 non-hazardous injection wells, and that is going to be the ones on the far left here in the red text. Class 1 non-hazardous. When a lot of people hear the word injection well, they'll think of class 2 saltwater disposal wells for oil and gas. These are completely different animals, so they're totally different in the regulations. They're totally different construction requirements. Class 1 wells have a robust construction requirements, monitoring and testing requirements that protect underground sources of drinking water, and we're going to walk through some of those today. And although today I'm focusing on class 1 wells, SCS, we do permit and work with class 6 wells. We've prepared multiple permits in multiple states for supercritical CO2 injection as well. So if that's something you're interested in too, you can talk to me afterwards. Here's my green box. So this diagram is put together for CO2 injection in class 6 wells, but the concepts are the same for wastewater disposal. So anywhere where you see a yellow line going down into the rocks, you can just think of that as your wastewater stream instead of CO2. So this kind of just helps provide that cross-section diagram that gives you a visualization of where your waste stream is going. So being a geologist, I'm going to start off with some of the geologic components of an injection system. The first one being your injection zone. That's the thick, permeable, porous unit that is accepting your wastewater. And then above and below that, you have nearly impermeable confining units, which are also thick units, but these have very low permeability. Whenever you do the math on the permeability of these things, these confining units, it's on the order of thousands of years to move for fluids to move a foot or a few feet across these things. And these confining units are hundreds of feet thick typically. So they effectively act as lids containing your wastewater in that injection zone. So let's talk a little bit about how they're constructed. On the right there, you have a vertical cross-section view of an injection well, and you can see the multiple strings of casing there with the orange bracket on the right. And those telescope down into your injection zone. So you have a very large diameter casing, and then a smaller one and a smaller one. And then ultimately you have one that goes all the way into your injection zone. And we'll talk a little bit more about that in just a second. But you can see the perforations towards the bottom of the well, below that red thing that's your packer that holds your tubing. And then you also have your nearly impermeable confining units, or the gray horizontal units that I mentioned. And And then on the left, you have a horizontal cross-section of the well, and that brown line on the outside represents the rock formation that you drilled your borehole through. And then inside of that, you have a layer of cement that encases your surface casing. And inside that surface casing, you have another layer of cement that holds your intermediate casing. And inside that intermediate casing, you have another layer of cement that holds your long string casing. So you have 6 physical barriers there to prevent fluid leakage into underground sources of drinking water. Now remember that long string casing goes all the way down into your injection zone, and inside of that you have a freshwater filled annular space that has your injection tubing in it. And that freshwater filled annular space is always kept at a higher pressure than your injection tubing. And your injection tubing is what actually conveys your wastewater down into the injection zone. So if there was ever to be a leak in that injection tubing, the fresh water would go from the annular space into the injection tubing into your injection zone, which remember is confined by those upper and lower confining units. So I touched on at the beginning, there's also robust testing and monitoring plans associated with these wells. There's continuous monitoring of the annular pressure to make sure that that is staying above your injection tubing pressure. There's continuous monitoring of your injection rate and your injection pressure. And there's alarm settings on those to where if they go out of a range that indicates something might be wrong, it will automatically shut in the well and stop injection. And then you also have annual and typically on a 5-year cycle testing plans that test for the 5-year cycle testing plan is your mechanical integrity to make sure that you don't have any leaks or fluid flow out of the injection zone. So who regulates things and where? In the darkest green, you have Louisiana, Wyoming, and North Dakota. And those states have primacy over all 6 well classes. Louisiana just got primacy on the Class 6 wells earlier this year. And generally, whenever you have state primacy on administering these programs, you have a more streamlined, smoother permitting process. And in the medium green, those states have primacy for multiple well classes. That usually means Class 2 and Class 1, and then maybe some others. And then light gray is EPA administration of the EUEC program, which doesn't mean it's not possible there. It just means we'd be dealing directly with the EPA instead of a state regulatory agency. And these numbers show the count of proposed and active and inactive Class 1 wells in each state. You can see that they're primarily focused in Texas, Wyoming, California, Kansas, and then Florida being the 800-pound gorilla in the room with 343. And that's at least partially because there are a lot of municipalities in Florida that have wastewater disposal wells for municipal wastewater. And there are so many in Florida because of the especially suitable geology there. So if you don't see a number on your state, that doesn't mean it's not possible there that we can't put one in there. It just means that there aren't any there right now. So where can we put these things in? This is a diagram available online from the USGS that looks at all of the major geologic basins in the United States to see if there's suitable geology for CO2 injection. So CO2 injection has more stringent pressure and depth requirements. So anywhere that's in gray or in orange is suitable for has regionally suitable geology for Class 1 wells. And if your particular facility isn't in one of those spots, it doesn't mean it wouldn't work. It just means we need to take a little closer look. But this is a really good, quick gut check of, is it feasible? Do you have the right geology? So we touched on suitable geology, proper well design, monitoring and reporting, and whenever you combine those with the environmental justice review, which ensures that disadvantaged and marginalized communities aren't disproportionately affected by the project, and the financial assurance requirements, where you have to establish, it's usually a trust fund, for the value that it would take to plug the well. You have to establish those funds before you even start drilling the well, so that there's money to plug it if something were to happen. And all of these things combined provide a robust protection of groundwater resources. So, Class 1 well is a large capital expenditure project, but we manage that cost with phases. Our first phase, we start with a feasibility study that takes 1 to 3 months, usually costs about $10,000 to $30,000. That just confirms your suitable geology. You have a regulatory agency with a pathway to a permit. Then we would move on to our permitting phase, where we engage with the regulators and start writing our permit application. That can take from 6 to 24 months, depending on your regulatory agency, your the complexity of your geology, the availability of geologic data, and your public engagement. You can have public meetings in some states that may add some time onto your permitting process, and that permitting usually costs about $50,000 to $200,000. And then once we get our permit to construct, you're looking at 6 to 24 months to get your contracting with your driller, get your materials, do the actual drilling, complete the well, and build your surface facilities that are associated with the deep well. And that usually is about $1.8 to $6 million, depending on where you are regionally, the depth, and we'll touch on those a little bit more on the next slide. And then once you're done with your startup, you're ready to operate. And those annual operating costs are relatively low, and most of those are associated with operating the surface facilities that accompany the deep well. And whenever you run these things appropriately, you have an asset that lasts 20 years and usually more. So taking a look at some of the variables and the costs in a couple different places in the country for drilling one of these and constructing one of these. A rough budgetary estimate number for most of the country is $1,000 per foot. So if you have to go down 3,600 feet in southwestern Illinois, down there second from the bottom, the actual cost for a project that we did in southwestern Illinois came out to $3.3 million, which is pretty close to that rough budgetary $1,000 a foot estimate. Same for Kansas, same for southern Illinois. Now Florida is a little bit different. Florida, you estimate $2,000 a foot for that rough number because they have larger well bore diameters, and those larger well bores, they take longer to drill, they take more equipment to drill, they take more materials to construct, so those are about twice as expensive. But you get much higher disposal rates with those. You can see that it's 2 million gallons per day in South Florida versus maybe half or something less than half of 1 million gallons per day. And then also pressure. The pressure is going to influence your operational costs and some of the construction of your surface facilities costs. In Florida, these things operate at very low pressure. You don't need very strong pumps. You don't take a whole lot of electricity to run those pumps. In southern Illinois, those were some relatively high pressure wells that we installed some relatively expensive pumps for that take a little bit more electricity to run. So let's talk a little bit about the regulatory considerations. In many parts of the United States, you have zero discharge facilities, so NPDES isn't an option. We've worked with some power plants that this is their situation, so this was enabled them to handle their wastewater and still maintain that zero discharge facility status. Other places, they have very strict water discharge criteria, and then also your NPDES permit cycle changing every 5 years, your analyte levels, them changing that on you. You don't have to worry about that with deep wells. They're a 10-year permitting cycle, and because you're disposing these things into deep saline aquifers, they don't have the same level of stringent concentration requirements on your waste stream. So I already touched a little bit on some of those reservoir geologic requirements, but commonly, what you're looking for is something that can accept 200 gallons per minute to 2,000 gallons per minute, somewhere from 0 to 2,000 psi. We can go higher pressure, but that does start to run up your pump cost and your operating costs. Something else that we haven't talked about yet is we do a geochemical model to look at the compatibility of your waste stream with the fluids that are in the injection zone. Because you don't want that brown stuff over there on the left precipitating downhole in your $3 to $6 million asset, and then you have to go and do a $500,000 workover to fix that. And if you don't properly tune your surface facilities and make your proper chemical adjustments, then it's just going to happen again. So as part of that permitting process, we do a geochemical model where we look at the interaction of the fluids that are already in the injection zone and the constituents in your waste stream to make sure that we can take care of dropping out any of those dissolved solids before they go into your injection well. Another thing that we do is we make sure that we have a biocide added to the waste stream so that you don't get gray fuzzy stuff growing like in the bottom right here. That was in a well in Florida that did not have proper biocide added to their well. It's an expensive workover to fix that. It can be fixed, but that's a cost that you do not want to have. So regionally, those surface facilities are going to look different. In Kansas, where I'm at, they operate under gravity injection. There's no injection pumps. It just sucks it down on a vacuum. So you don't have the operating costs or the maintenance costs for pumps, and your surface facilities are pretty minimal. You might have a little bit of the pre-treatment, solids filtering, maybe some pH adjustment, adding your biocide, but relatively minimal surface facilities. When you come to a case like in Southern Illinois, where we had those very high injection pressures, you need some of these really big pumps like this blue one down on the left to get those higher injection pressures. But across the board, anywhere, you're going to want to have that biocide addition, probably a pH adjustment, and you're going to check and see if you need to remove any of those dissolved solids to make sure that you're not harming your asset. So when we think about doing these at power plants, these are very busy facilities. There's a lot going on. Sometimes you have space constraints. Generally, we like to have 2 acres to set up a rig and drill a well, but we just finished a project in northeastern Kansas where we set up a rig in a half-acre lot. It was tight, and some of our vendors were a little hesitant about it, but we made it work. Once you're all done with your drilling and construction, you have about an acre between your injection well and the surface facilities. Looking at things from a facility level, we want to think about the water balance in your facility. Do we want to size this well for peak demand, or do we want to just operate it 24/7 and have equalization tanks? Are you going to be changing your processes? Are you going to be adding processes that are going to change the geochemistry or the flow rate in the future? Or are you going to even go through decommissioning and close your plant down? That's going to change your chemistry, but you're still going to need a wastewater management option. That's what we're doing near Marshall, Texas right now. We have a power plant that's undergoing decommissioning, and we're going to put one of these in to handle their CCR waste stream. So there's also some avoided costs associated with these. Whenever you're done with the injection well, you run your integrity testing and do the required due diligence, remove the downhole assembly, remove that tubing, and you fill it with cement and walk away. There's no post-injection site care. So you release that bond, you have nothing tied up. There's nobody going out there checking on things. There's nobody checking groundwater monitoring wells around these things because you've already shown that this well has integrity and is not leaking. So we've even worked with some clients that we've turned this into a revenue opportunity. We had a coal-fired power plant that was mixing their CCR leachate and other chloride waste streams into their fly ash and conveying it out to their CCR landfill. Once we took care of those wastewater streams, they were able to market 100% of their fly ash. They were already marketing about 20 to 50% of it, but once we did this for them, that was an additional $300,000 a month coming in for them. So that well paid itself off in less than 2 years. And we have a lot of situations like that. We have others where landfills are looking to accept third-party leachate, and they use the fees from disposing of third-party leachate to finance the construction of the well. And that depends on how much third-party leachate you want to accept, how much you can accept geologically, but the scenarios that we're looking at for a client right now, the return on investment is somewhere between 2 to 6 years, depending on how much they want to accept. And then additionally, if you close your facility or you change your process and no longer have that waste stream, you have a marketable asset. People are always looking to get rid of wastewater. There's people out there looking to buy these things in some cases. So I'm by no means an expert on PFAS, but I've looked into the 2021 to 2024 strategic roadmap for EPA action. And their second central directive is they want to restrict and proactively prevent PFAS from entering the land, air, and water at levels that can adversely impact the human health and the environment. Well, deep wells are a great option for disposing of PFAS waste because it removes the waste from those systems that they want to limit the entry of the contaminants into. And in PFAS, and in the EPA's PFAS interim guidance from 2020, deep well injection was actually the first preferred wastewater disposal option over incineration because it offers more uncertainty on what happens with those contaminants. With incineration, there's the effectiveness of it's not 100% understood. There might be new PFAS compounds that are created by partial combustion. Whenever you look at just recirculating in your landfill, the waste mass will retain most of that PFAS, but about 10 to 25% of it is still coming out in your landfill leachate, and that can concentrate over time. So when it comes to SCS and our value proposition for these projects, we have a deep understanding of the industry drivers of these. We've worked with the casing providers and understand how this fluctuations in the steel market can affect the availability and the price of your casing. I've worked on UIC projects in 9 different states. We have good relationship with the regulators across the country, and have a very good history of engaging with them and working through any kind of permitting challenges with them. We are able to offer a turnkey project delivery. So between our deep well team and our liquids management strategic initiative, the deep well team can do all of the feasibility, permitting, construction, and commissioning of a deep well. and our liquid management team is able to do the chemical analysis, look at your process, and design and procure a surface facilities treatment system to go alongside your injection well. So just to touch on some of the high points here that we've covered. Using a deep injection well for fluids disposal offers a permanent wastewater disposal option, thousands of feet below your sources of drinking water. You have redundant systems to protect the environment and drinking water resources. And something I didn't mention yet, but this injected water, this wastewater streams are often of higher quality than the water that's already in these super saline deep aquifers. So the water that's down there many times is hundreds of thousands parts per million TDS, whereas your waste stream might only be 1,000. And like I talked about, these are assets that last 20 years or more whenever properly managed. And any one of those situations that I talked about, whether it's turning your well into a commercial well or freeing up real estate on your facility because these things have such a small footprint compared to like a leachate pond or something, or freeing up other processes to market other products. If you get any one of those combined into here, the return on investment is very short. Well, that's all I had for y'all today. I'm going to open it up for discussion if anybody has any questions.
I got a million, but I'll take you.
Okay. Do you want to start with one?
Typically, on the O&M side, you showed 150 to 500K annually.
Mm-hmm.
Is the plant sites typically operating these, or is it someone else? Or what is involved in that operation?
So you'll have management of the surface facilities. You'll have solids filtration. You'll have the systems that adjust the pH, that add the biocide. The facility manages those, but we help them with the startup and commissioning of those facilities to make sure everything's tuned just right for the injection well.
On the permitting side, I knew you guys were doing the one in Marshall. We had a similar situation very there. And I've seen UCC stuff there too. Like I said, what's the permitting time frame that y'all are doing?
Here in Texas, we talked to the TCEQ, and it's somewhere around 12 to 14 months, I think, for them to have a permit turned around. And that's not accounting for if there was public engagement, which can add a month or two.
The other question I have, there's lots of oil and gas activity in that part of the world. And also have some other injection wells, the class 2,
Mm-hmm.
the same market. Is there opportunities at some of these facilities
To inject oil and gas wastewaters?
to mix them in there with them? I don't know. I don't know anything about this, but this is
Okay.
on our plate.
No, I just want to make sure I'm giving you a good answer.
Can I go to a class 2 well and dump some water out and add on?
No, you cannot, because class 2 wells are only for exploration and production wastes. So salt water that comes out of the oil or other exploration related waste, drilling mud, that kind of stuff. But yeah, that is something we ran into with that project, where we wanted to make sure that we weren't pressuring up the reservoir with the class 2 wells nearby. So we're targeting a couple of injection zones.
Injection wells are taking a lot of heat, seismic activity.
Mm-hmm.
What kind of kickback are you seeing from regulators on that? Pressure? What are their safeguards and mitigations that they're trying to influence that?
Yeah, I'm glad you brought that up because if nobody had any questions, that was going to be the thing I talked about next. So there are regulators that get pretty nervous about the seismic activity thing because they don't want to be the one to authorize a well, and then all of a sudden there's an earthquake and everybody's breathing down their neck. But every single one of these Class 1 wells, as part of the permitting process, you do a seismic risk evaluation. You look at the history of seismic activity. You look at the geology to make sure that you're not in a fault zone or a zone of active seismic, an active seismic zone. And then there's well construction techniques that can also help significantly reduce that risk, like pulling up off of the basement. So the basement rocks are different than the rocks that we're injecting into. These are billions of year old rocks that have deep faults that can cause the larger earthquakes especially, but they're associated with the smaller seismicity that we see a lot of times with induced seismicity. So making sure that you have a good lower confining unit that separates you pressure and fluid flow from the basement can significantly reduce that. They've seen that in some of the Class 6 wells. They've published papers on that where they completed one well and it was closer to the basement and they saw a lot more microseismicity. We're talking about stuff like less than 1 that you would never ever be able to feel. And then they completed one just maybe a mile away and they had pulled up 50 to 100 feet off of the basement and they had a baffle for pressure that reduced that pressure communication into the basement, and they saw almost none of that microseismicity that they saw at the other one. What's that?
Rattle and give it a soft line.
So that's just a few of the things. Any other questions? I'll say a little bit more about the induced seismicity then. So a big problem with the situation in Oklahoma is the sheer volume of Class 2 wells. Whenever you have hundreds of Class 2 wells injecting a million gallons a day or something, that's a significant change in the hydrostatic environment in the subsurface. A lot of times these Class 1 wells are not located in those big oil and gas fields where you have hundreds of Class 2 wells. You might have a few around them, like in that case that we were just talking about, but whenever you only have just one Class 1 well, it doesn't produce the same level of changes in pore pressure. If that's all, I'll conclude.
Thank you. Thanks for filming. That concludes this segment. Thank you for attending.
I'm making it's so nice. And then I'd rather text them like that was the time you're connecting with a plane to come in. Nice meeting you. Yeah, I don't need to go off, but you know,
That's my question.
Yeah, I met, I was a general set up over there first.
Oh, good,
A few weeks ago. Well, first, I mean, it's basically a stopgap until they get to the right.
They are, yeah. I had like
You gotta get some. I grew up fishing on that lake.
Okay, well, it's pretty cool.
Oh, they did?
We're in a record line on there.
Our air guy. Yeah, I had a good discussion with Joseph.
Yeah.
Yeah, he and I, we're on the same page.
Oh, good.
Yeah.
Well, that makes one of
I
you.
told him, you have to come on the
Well, that's good. Am I allowed to tell him that, or should I give him
You
some?
can.
I'll tell him. All
Were y'all here yesterday too? Or
right. Yeah, he's a good boy. I'm glad we got him.
I just work in
Yeah.
a relatively small group of
Yeah.
very important, like, like 12 people.
Yeah, we operate several of our facilities already.
I think his flower pieces are
But when we get into lab,
Okay.
I mean, you're talking tons of water, or gallons of water, you're talking, you
It's
know,
not just.
500 feet.
No, they mostly,
You know.
actually, 50% of what we do is
Okay.
design construction.
Hundreds of millions of gallons.
Yeah.
Hope I wasn't harassing.
No, you're good. You're good.
Well, you guys have done some good stuff,
Yes.
right?
Oh, really? Pleasure to see you again.
I took a picture of you, so I'll like send it to you by text message.
Okay, thank you.
Yeah.
Appreciate it. You got my good side?
Big deal.
I
Right, exactly, yeah.
I think y'all use some of our data too.
Yes.
I took Monte's and
Yeah,
adapted it,
that's
added some stuff.
But no, I just was curious, my question is.
No,
yes.
no.
We'll go to the court, we'll clean it on.
Right,
Sorry,
right.
I was in here.
Yeah.
But you know, something like that,
I
that's
missed
been
it.
hard.
It's red when my
Didn't say it here, but it's also.
Just in time.
Yes, exactly. Yeah. And so,
How the hell did you?
yeah.
Just.
Yeah, and I've
Especially if
done
you're trying to reduce harm.
yeah, I performed this and that's like, it's almost like a back of the envelope, it's not as intense as that, but you could if you wanted to, put that in the database, and you can get not just like, greenhouse gas emissions, you can get any sort of emissions, and then you can show that to the state. You can show that to the state, you can show that to, local agencies. They wanna see that information.
Yeah,
You know,
it's crazy.
it's not just like, you know, the law says you have to do this, and so that's the most environmentally friendly. There's other considerations that like could be reasonable.
Yeah, I mean, that's just diesel fuel, 75 million miles.
Yeah.
And that's just part of it, because to do it was gonna cost over $1 billion.
Yeah.
We're good.
Yeah. Awesome.
Well, hey, thanks a lot.
Yeah.
No, I'm here. Chambers. Yeah, this is amazing. We've been talking about this. We tried to do an injection well, safety out of their time. Probably 20 miles. And I don't know what happened to the 80s. And so the stigma with us is, we tried this before, we're not doing it. We've lost upon some of the CCO regulations. We have a facility in Monte. It's, but, you know, we're looking at maybe building a pond. Well, hell, pond. And in my mind, that particular plant, we want to keep out. It's all over the place. I mean, if we shut down, we got all these, we operate. So if you could use a well as a water management tool when you're operating and have it in the body to just drink and then put it on.
Yeah. Yeah, that facility in Marshall, they don't plan on having anybody on site practicing enclosure. We're gonna work out some details of that with the regulators. But,
And so, and you said once you plug it, there's not like on the back.
no post-injection site.
So, no scheme that does no
Yeah, that's where the focus is. We have people remote all across the country.
At least we deal with some of your guys here. Shuttle type guys. But I'm really interested to talk some more about it. I'm an environmental guy. I'm not and this is what I've been telling our we got populations here, Ohio, it's not yet big. Instead of paying, we're looking at treating water.
Yeah. So I'm originally from Illinois. Yeah, you never know, they might change your effluent.
Yeah, well, and 825 is, I'm just glad I deal primarily with Texas. Anyway, yeah, I think I'm gonna put there in your. Georgia, we do because we've got, like I said, I don't know. We've got 3 that will have perfect kitchen, 2 of them operate. We're trying to figure out. He took ELG. That's going to be a question. That right there is something that's a solution. At the end of the day, what kind of volume can you?
No, it's not imminent, but it is dependent on your geology, and we look at that as part of the permitting process, is the pressure window. Fracture the rock.
But I mean, you're showing like half a million gallons a day.
Yeah, that's
on average.
That should be pretty easy to do outside.
You did that for 40 years.
Yeah, so we do pressure modeling. See how much that pressure will
You cite these things. So, I think do you ever really